Welcome back, guys. Today we're going to look at mutations. And last time we talked about transcription translation, going from DNA to a strand of RNA, and then from RNA to a protein comprised of amino acids. So today we're going to talk about what happens when there's a change to this DNA and how that change is reflected then in the resulting protein. Right? If there's a change to this DNA, that results in a change to perhaps the amino acids that comprise the protein, and all those amino acids have different properties, which can cause our protein to become misfolded or change shape, and that has an impact on how that protein functions. All right. So we're going to, again, we're going to write some notes down, we're going to look at some concepts, and we're going to look at some examples, and hopefully you'll have a good understanding of this when we're finished. Okay, so here's the space that we're going to use to kind of take our notes down and talk about these concepts. You're free to write these down with me, or if you just want to sit back and listen and watch, that's fine too. I'll make an effort to post the actual finished notes at some point in time. But again, it's going to be best if you go through and just kind of work through this slowly with me, rather than just look at the completed document without any context. So we're looking at mutations. And a mutation is just a change in the order or the sequence of that gene. So we'll say a change in gene sequence. In parentheses, we'll put order, the order of the nucleotides. I'm just going to write that here. The order of the nucleotides. And there's a couple things that can cause this change. It could be an error. So these changes can arise from errors in replication. So that process of making more DNA when a cell divides, it's got to replicate all its DNA in S phase of mitosis. So there's mistakes that are made there, and if those mistakes aren't rectified, that can manifest itself as a mutation. Or we know about all kinds of different mutagens. Those are things that alter DNA, like radiation, whether that's UV radiation or X-ray radiation or gamma radiation. All those things can damage and change DNA. Could be chemicals like asbestos, like dioxins, that can damage and change DNA. So all of these things can eventually lead to mutations. So we have some different varieties of mutations that we're going to look at. And the first one we're going to look at is called a frame shift mutation. So a frame shift mutation. And a frame shift mutation is when there's an insertion. So we have an insertion. So we have a base that's inserted or deleted. So insertion or deletion of a nucleotide into the DNA strand, and it moves the entire coding frame. We'll talk about what I mean by that. So the ribosome is reading the RNA strand, it's reading the RNA, but that RNA is coming from the DNA. So the RNA strand is being read in sets of 3 in codons, right? So the ribosome, we're going to say, is reading the code as a set of 3. Okay, we call those codons. So if you insert a base or remove a base, that's changing that whole coding frame. We're going to look at an example. Again, what happens is most and or all of the amino acids after that insertion or deletion are going to be different. They're going to be changed, because you change that coding frame. Now, why does that matter? What effect does that have? Is all those amino acids, they have unique properties. So if you're getting different amino acids, you essentially are going to have a different protein. Now, why does that matter? Well, if a cell or a tissue is depending on a certain protein to do a specific function or job, and now you have a different protein, it's likely that you have a loss of that function. So that cell or tissue now no longer has that function being carried out. So let's check out an example. Okay, so here's the sheet we're going to use for our example. And we have an original DNA sequence that I'm going to go ahead and box right here. And here's our DNA sequence. We can see that our RNA sequence is here. So we've taken the DNA and we've decoded that into RNA. So TAC, it helps if you break this up into sets of 3. So TAC is encoded AUG. And we have our next one here, our next one here. I'm going to actually make this a line tool. And then you can see the RNA, we've used the codon table, and we've assigned all these amino acids that go with those codes, right? So we're going to look at an insertion first. So I'm going to go ahead and box that insertion. So here is the insertion that we're going to look at. Okay, so let's go ahead and take my line tool. And I'm going to split this up into groups of 3. Just like so. And the first thing I recognize is that I've got an extra nucleotide hanging out here. That tells me that there's probably been a nucleotide that's been stuck somewhere in this sequence. And I want to find out where that is. So I start comparing the DNA. TAC, that's the same. GTA is the same. GTC, it says GT or TGT, and then I have a C. So this T is, let me get the right tool. So this T right here has been inserted, right? If we compare the strand above, where it goes TAG, TA, and then the G's over here, this T has been inserted. So what does that mean? If we look at the amino acids, pick a different color here. If we look at the amino acids after that insertion site, they're all different than the amino acids above, right? Methionine and histidine are the same, but then all of these amino acids are now effectively different because this code is being read differently. So that's what we see with an insertion. And the deletion is going to be much in the same way affected. So let's go ahead and get a look at this. So we're looking at this deletion, and we're going to go ahead and break this up into groups of 3, just like we've done. So break this up here. All right, so broken it up, and I can see that I'm missing, and there's no nucleotide at the end here to complete this triplet like above. I'm clearly missing one, so I'm just going to take this arrow and try to figure out where exactly that would be. So TAC, that's the same. GTA, that's the same. GTC, that's the same. The CCT and its ACCT, so that A appears to have been deleted from that position. And when I started looking at this, these 3 amino acids that begin the sequence are the same, but the ones that follow then are going to be different because that reading frame has been shifted. So these amino acids then after that deletion point are all going to be different. And if we compare that to the top, that's kind of what we're seeing. So let's talk about the next type of mutation that we have to cover here. All right. And we're going to look at something called a point mutation. Point mutation. And this is often known as a substitution. Substitution. And there's going to be 3 different varieties of point mutations. So the first one we're going to look at is called a missense. Missense. And a missense is different than a frame shift because in a missense, it's a single base, not an insertion or a deletion, but a single base substitution. So it's a substitution. And it's going to result, we'll say that results in a new amino acid. Okay, so it's a single base substitution that results in a new amino acid. Now, why does that matter? Well, if you think about this, we talked about amino acids having different properties. So if you swap out one amino acid for another, there's a likelihood that that protein it is going to fold differently. So that protein may be misfolded. So it might fold differently. So that protein might be misfolded. And then that shape change from that misfolded protein, it can lead to a loss of function or a gain of function in this case. Typically, it's going to be a loss of function, but in some rare circumstances, that protein is actually slightly more effective with that different amino acid and that modified shape. So that's where we say that's where we see like gain of function evolution coming from, right? Where a protein that was once doing a particular job has been slightly modified, and now it's actually more effective with the various selective pressures in its environment. So that's where we can see evolution kind of starting to pop up here in that particular type of mutation. Let's get a look at that. All right, so here we are back with our handout, and I'm going to go ahead and box in a new original sequence. So here's my new original sequence, and I'm going to go ahead and break it up into sets of 3, which again I recommend doing. Allows you to analyze this with greater ease. All right, so there's my original sequence, and I'm going to look at this missense mutation. So let's look at this one here. So start breaking this up, groups of 3. I'm going to look for that mutation. So again, TAC, that's the same, CCT, same, AGG, same, AAA, AAT. So here's the substitution. That T has been subbed out for an A, which UUA is leucine and UUU codes for phenylalanine. So that's the difference. So this is the change, this amino acid difference, leucine instead of phenylalanine. And again, it's likely that this protein is going to fold differently because the properties of leucine and phenylalanine aren't the same. Okay, so that would be our missense mutation. Let's look at the second variety of point mutation here, and it's going to be what we call a silent mutation. So a silent mutation. And it's still a single base substitution that results in the same amino acid. And we'll show you an example of this one. If you get the same amino acid, you have essentially the same protein, right? Because it hasn't altered the amino acid sequence. The primary structure of the protein is still intact. Let's get a look at this one. All right, so here we are back at our example set, and I'm going to break this up. I'm going to use a different color, maybe red. Break it up into groups of 3. And I start looking and trying to find where that mutation is at. So TAC, that's the same. CCT is the same. AGC, we have AGG, so that's the change. That C has been subbed out for that G, or sorry, this G has been subbed out for this C. So what does that lead to? UCC is now coded UCG, and our amino acid serine is actually the same as the amino acid serine here. So the code did not change. That's because we have 64 codes and 20 amino acids. So we have redundancy in the code that minimizes the impact of this mutation. Now, does that mean that there won't be any effects? Not necessarily. because the RNA is changed, right? This RNA here is changed. So there may be issues in terms of how long that RNA is allowed to stay in the cytoplasm for the ribosome to translate into protein. But the protein itself is not going to change. The protein is the same. It's just the amount of protein and the timing as it's produced because of the change of the RNA can still have a role or an effect. Again, that's a silent mutation. So let's look at the last of the mutations that are point mutations, and that's going to be a nonsense mutation. So a nonsense mutation. And this is a single base substitution that results in an early stop codon. So a single base substitution that results in an early stop codon. So this mutation has caused a code to become a stop code, which means we're not going to get amino acid there. We get a release factor, so we get a shortened protein. And that shortened protein is, there's no way it's going to do the same job as the original protein, so we're getting a loss of function. So we'll give you a look at a nonsense mutation here. So here we are back to the example set, and I'm going to go ahead and get my line tool back out. And we're going to break this up into groups of 3. And I'm going to get my circle tool. So TAC is the same. Here we go. This C above has been mutated with an A, substituted with an A. So now we get GGA being read as UGA, and that UGA, that codes for stop codon. So instead of getting glycine, we have a stop codon. So then the amino acids that should follow here don't, because the ribosome stopped translating because it was told to because of that mutation. All right, so that's a nonsense mutation. Now, if we look at this bottom strand here, you'll notice that we go through, let's just go ahead and cut it up. Again, break it up into groups of 3. And we're looking for a mutation. And it's very early, actually. So TAC has been mutated to TAG, which changes this codon. And now we don't have a start codon anywhere in the strand, so the ribosome is not going to bind and start bringing in amino acids because there is no start codon. All right, that's really, really important. So finally, to finish this up, the last thing we'll look at is something called a chromosomal mutation. Chromosomal mutation. And with a chromosomal mutation, we're talking about, entire pieces of a chromosome that are being deleted, duplicated, inverted, moved, in which case we call it a translocation. So, a deletion, duplicated, inversion, translocation of a section or segment of a chromosome. And we're talking not just one nucleotide, but we're talking thousands of nucleotides at a time. So these are big time issues for a cell because you're not just removing one nucleotide and getting one affected protein, but you might be affecting thousands of protein products. So that's a really, really, really big issue. And we're going to sketch out, again, kind of what this looks like. So let's say that we've got chromosome number 8 here. we're just picking an arbitrary number, right? And chromosome 8, let's say it's made of segments A, B, C, D, E, and F. And then we have chromosome number 9 here that has segments 1, 2, 3, 4, and 5. So a deletion would be like if on chromosome 8, section B just was deleted. And this can happen during meiosis, which we'll look at later, where the chromosomes are supposed to detach from one another. If that doesn't happen appropriately, then a piece of this can end up being deleted from a potential cell, sex cell. You get a duplication where there's an additional piece of B that's duplicated again, or B and D switch and get swapped, or A maybe ends up down here on this other chromosome. Again, that's a really big issue. So that's just a look at mutations. Let me know if you guys have any issues. I'll be posting an assignment that goes with this later this week, probably Friday. That'll be due next week. So shoot me an email or comment if you have any questions about this. We'll see you next time.